All right, we're now going to start with a quantitative description of gases. We can use this equation, which is the ideal gas law, PV equals nRT, which we're going to remember that pressure in this, pressure in this case is abbreviated with a P, volume with a V, moles with a lowercase n. This is indicative of the gas constant, which is 0.0821. The units of this are liters times atmospheres per mole per Kelvin. I like to call this the chemistry gas constant. You should recognize that there's an equivalent form of the gas constant with different units that we will sometimes use. I'll call this the physics gas constant. This is 8.314 joules per mole per Kelvin. And of course, T is temperature. As we look at our units of the gas constant, this is the one we're going to use in the ideal gas law. So we're going to use the chemistry gas constant in the ideal gas law. We should recognize that our pressure is going to have to be in units of atmosphere. Our volume is going to need to be in units of liters. Moles is going to be in units of moles, and temperature, as I said previously, that's going to need to be in units of kelvins. That's always true with the gas laws. Temperatures need to be in kelvins. So the units of the gas constant are going to tell you what your units need to be when you're doing these calculations. If I take the ideal gas law, PV equals nRT, and I divide both sides by by NT, I get PV over NT is a constant. And what this tells me is that given any combination of these units, I'm always going to end up with the same thing. And so I can write this in this following way. Let's say we take our gas with a pressure at condition 1, a volume at condition 1, number of moles, condition 1, and the temperature in condition 1, like an initial condition. That's going to be equal to some final condition that I change all of these variables, because it's always going to be a constant. So this is going to be R, this is going to be R. So of course they're going to be equal to one another. And so from this fact, we can derive all of the other gas laws that are used. For example, you might see this equation, P1 V1 equals P2 V2. This is the relationship between pressure and volume of gases under some initial and final condition, given moles and temperature are constant. In other words, if these aren't changing here, then of course we can just ignore this portion of the equation, and we get P1 V1 equals P2 V2. We can do this with all sorts of stuff in the equation. Of course, there's an equation that relates volume and temperature. Volume and temperature are going to show a relationship if pressure and moles are constant. We can see from this equation here that that's going to look like this. V1 over T1 equals V2 over T2 if, well, let's see, pressure and moles are constant. And then every once in a while we do a problem which we call the combined gas law. This one's, by the way, this one's called Boyle's law. This one here is called Charles's law. And sometimes we use what we call the combined gas law. That's if the only thing we keep constant is moles, so we can ignore the moles in these equations and everything else varies. So the combined gas law would look like this. P1 V1 over T1 equals P2 V2 over T2, of course, if your moles of gas are constant. All right, we're going to use these in a couple problems. The first one says we've got some air in a syringe at 20 degrees Celsius. So here's my syringe. Got a plunger here. And there we go. The gas is in here. Looks like it's at 20 degrees Celsius. And its volume is we'll put the syringe plunger like right to there. All right. So this is how much gas is in the container. Its volume is 25 milliliters, and we're going to heat it. And we heat the syringe, of course, the gas is going to expand, and we're going to heat it to 37 degrees Celsius. And what we want to know is what is the new volume? What's the new volume? Well, if we look at our equation, P1V1 over N1T1 is P2 V2 over N2 T2, we notice that the pressure on the syringe, that's always going to just be atmospheric pressure. That's not going to change. So our pressure is constant. We also know that the amount of gas isn't going to change as well. It's sealed. So your moles is going to be constant. So we're going to use this equation. V1 over T1 is V2 over T2. And the only thing that we don't know is the second volume. So we just set it up. We just plug things in. This is the initial 1 conditions, and this is our final 2 conditions. So let's see. I'm going to plug in this temperature, of course not in this form, because we want to recognize anytime we use gas laws, we want to use Kelvin temperatures. So remember, 273 plus our Celsius is going to give us our Kelvin temperature. So our volume 1 is 25 milliliters. Our temperature 1 is 293 Kelvin. We're going to set that equal to our new volume, which we do not know. So I'm just going to put a V over here, V2 if you like. And then we need to divide that by our Kelvin temperature, 273 plus 37. That's going to give us 310 Kelvin. Plug that in. Of course, I want V2 alone, so I multiply both sides of this equation by 310 Kelvin. Kelvin's going to cancel Kelvin. My volume is going to be in units of milliliters. And all I got to do is figure out what the temperature is going to be by doing the math. 310 times 25, divide that by 293, should give us 26.5 milliliters. So our volume is going to increase slightly from 25 mils to 26.5 mils on warming. All right, let's try this problem here. We've got a scuba diver at the bottom of a lake. So here's our lake. Here's our scuba diver. And they're going to blow out a bubble. And that particular bubble has a volume of 100 milliliters. Let's see our initial conditions. Volume is 100 mils. The temperature is 6 degrees Celsius. And the pressure at the bottom of the lake is 1.5 atmospheres. That bubble is going to rise and hit the surface, or at least get close to it. So in final conditions, we want to know what the volume is going to be. We don't know what that's going to be. The temperature is a little warmer at the surface. We're going to call it 28 degrees Celsius. Looks like it's a summer day. And the pressure, of course, is going to be less because you don't have quite so much pressure as at the bottom of the pool, the lake. So it's going to be 1 atmosphere. So if we take our equation, P1 V1 over N1 T1 is P2 V2 over N2 T2. We see that 3 things are changing. but we're going to assume that the amount of gas in the bubble is going to remain constant. No gas is going to leak in or out. And so we're going to end up what's called the combined gas law. So that's going to be P1 V1 over T1 is P2 V2 over T2. We want to make sure we convert our temperatures to Kelvin. It's going to be 279 Kelvin and 301 Kelvin after we both add 273 to each of these. And then we can set up the problem. P1 is 100 mils. V1, sorry, that's V1. P1 would be 1.5 atmospheres. And we're going to divide that by T1, which is going to be 279 Kelvin. And that's going to be equal to P1, which is 1 atmosphere, times the volume that we're looking for, divide by 301 Kelvin. We got a little bit of math to do here. Let me go ahead and write these over again. All right, so we want the volume alone. So I'm going to multiply this side by 301 Kelvin to cancel this, and divide by 1 atmosphere to cancel this, leaving volume alone on this side. Of course, whatever I do to this side of the equation, I have to do to the other side of the equation. So we're going to go 100 mils, 1.5 atmospheres over 279 Kelvin. We got to make sure we multiply by this fraction just like we did to the other side. 301 Kelvin, divide by 1 atmosphere. Kelvins cancel, atmospheres cancel, and now we're just left with the math. Notice the unit that's left over is milliliters. And the arithmetic will be 100 times 1.5 divided by 279 times 301. Of course, divide by 1 is the same. It looks like the volume of the bubble is going to increase from 100 mils to 162 mils as it rises to the surface. All right, one more problem. Airbags generate gas through this chemical reaction. Sodium azide, on impact, an electrical impulse runs through the sodium azide and causes it to explode. It produces sodium in the solid phase and 3 moles of nitrogen gas, which is used to inflate the bag. On impact, it looks like we want to generate a pressure of 1829 millimeters of mercury. The volume of the airbag is 45.5 liters, and it looks like the temperature we'll assume is 22 degrees Celsius, which I'm immediately just going to convert to kelvins. That's going to be 295 Kelvin. We want to know how much sodium azide do we need to generate these conditions. So the equation we're going to use in this case is PV equals nRT, because I know everything except for moles. If we know moles, we can figure out how many grams of this we're going to need to stick in the mechanism. Notice we know pressure, we know volume, we know temperature, and of course in the ideal gas law, we're going to use the chemistry gas constant, 0.0821 liter atmosphere per mole per Kelvin. And these units are going to remind us of what units we need to use in the problem. And I see my liter is fine, but my pressure is not. Pressure here is atmosphere, but the pressure given in the problem is in millimeters of mercury. Of course, I already converted to Kelvin. So we need a conversion here. 1829 millimeters of mercury. We want to convert that to atmospheres, and we recognize that there are 760 millimeters of mercury in an atmosphere, noting that I put the millimeters of mercury on the denominator to cancel the millimeters of mercury on the numerator. 1829, we're going to divide that by 760. Looks like we want about 2.5 atmosphere pressure to inflate the bag quickly. 2.4 atmosphere. Now I can plug everything and figure out what moles is. So let's see. Symbolically, let's do this first. PV is nRT. I want to know moles, so I'm going to divide both sides by RT. Curses. Let's try that again. PV is nRT. Divide both sides by RT. This is what we want to cancel, of course. So we notice to find moles, we're going to take pressure times volume, and we're going to divide that by the gas constant times temperature. So let's just throw everything in here and see what we get. So let's see, my moles should be the pressure, which you might remember is 2.4 atmospheres. So let's pop that in. 2.4 atmospheres. The volume, that's got to be 45.5 liters. So we'll pop that in here. We're going to divide that by the gas constant, 0.0821 liter atmosphere for every mole for every Kelvin. And we're also going to need to divide by the Kelvin temperature, which we showed previously to be 295. On the denominator, inverse Kelvin cancels Kelvin. Atmosphere on the numerator cancels atmosphere on the denominator. Liter on the numerator cancels liter on the denominator. And we're left with an inverse mole on the denominator, which is a mole. It's good because that's what we're looking for. So we know we've probably set everything up correctly. Do the arithmetic. 2.4 times 45.5 divide by 0.0821 divide by 295. Looks like we're going to need 4.51 moles of nitrogen gas. Now notice, though, the question asked how much sodium azide is going to be necessary to generate this many moles of nitrogen gas. So we're not quite done with the problem. Let's remind ourselves of the chemical equation involved. 2 moles of sodium azide decomposes to 2 moles of sodium and 3 moles of nitrogen gas. So I'm going to start with the amount of nitrogen gas that we want to generate. We notice in our equation that for every 3 moles of nitrogen that are generated, 2 moles of sodium azide must decompose. And then if we want to know the grams of sodium azide, we're going to need to convert moles of sodium azide into grams of sodium azide. Well, what's the molar mass of sodium azide? Well, let's see. If we look on the periodic table, you notice that sodium is 23 grams per mole, and there's one of them. For nitrogen, that's 14 grams per mole, and there's 3 of those. Let's see, that's 65, yeah? Looks like 65 grams of sodium azide per mole. So I take my 4.51 moles of nitrogen, that cancels here. The moles of sodium azide cancel, and I've converted to my grams of sodium azide, which turns out to be 4.51 times 2 divided by 3 times 65. We're going to need 195 grams of sodium azide.